Greetings, welcome. So last we left off in the last video, we built this battery capacity tester with the Arduino. I'm having a little bit of trouble now with second channel, and I think I need to use nested if statements in the code. So I'm leaving the second channel. I'm not trying to do two batteries at once. I'm just doing one, but you know, it's working well. There it goes. It just every 10 seconds it spits out what your voltage is, how many milliamp hours it's gotten out, and then it will shut off when this thing, I've now set it to shut off at around 6.7, 6.8. So I'll just back up kind of and tell you the things I've been working on, what I'll try and do in this video, and you know, some of the things I've learned. So we're going to test the capacities and batteries, and then we're going to try and charge some batteries. Now we can actually look at milliamp hours out, milliamp hours in. Now one thing I think I've learned, I think my channel is being throttled, the reach of it. Maybe I'm being vain or paranoid, but I think it is, and I think I know exactly when it happened and whatnot. In one sense, I'm actually just delighted. I was like terrified in the back of my mind. So I went viral. But so you guys are the few, the proud, the nerds. And I'm not sure if the channel's going to grow much more from here, but I'm going to keep having fun with it. And this also, you know, gives me liberty to, you know, talk about cannibalistic cults and whatever I feel like talking about. To try to get back to the nickel metal hydride batteries. So we're testing the capacity of the batteries, and when we have 3 of them, I'll run one and I'll see what we're getting out on the other side. I spent some time recently trying to figure out, you know, having the spike come out, put it into a capacitor with a resistor across it, and then measure what you're getting out with the resistance. And I did a fair amount with that, all work and no play. And I realized today that it's all utterly useless, because, so let's pretend you have your cap out here that's catching a charge, and you have your resistor across it, and you're measuring. It's going to get a pulse, and it's going to go up, and let's say that the pulse is for 10% of the duty cycle. The other 90% of the time it's draining out through the resistance, and your meter is going to take the average of that time between the pulse and the rest of the 90% and spit out a voltage. So I was seeing, you know, well, I'm getting, you know, it's 15% efficient. I've got it up to 24% efficient. And that is wrong. It's better than that. If you think about it from the point of view of, you know, like the Q factor, and what's the Q factor, which should give you about what you're getting back. You know, I would think at least like 60, 70%, at least 50, something like that. And if you're trying to engineer off that capacitor resistor setup, it's going to point you in the wrong direction, because you'll start doing much longer pulses with, like, you know, like say a 90% duty cycle, only 10% off. And so now it doesn't have much time to drain out from the cap through the resistor, and you think you're doing great, except it's actually not as efficient. And you run into the same problem if you have a pickup coil going out to a bridge diode to a cap and a resistor. So I can't figure out any really good way to measure this without just doing battery testing. So for this first go around, we'll probably just use this trusty penny roll video rotor that I've been having so much fun with. And therein lies another tale of something else that I've figured out and learned recently. This rotor is nice because it doesn't have a lot of wobble like that. I think maybe like a 1/16 of an inch, and I've actually I don't want to dump the pennies everywhere. We got one bearing there, and then I've just kind of press this bearing in here, and I'll tell you what I'm talking about, both for why I like this and what I learned. So this rotor was where I was thinking I was going. It's 8 inches instead of 5 inches, and that space there is where that 2.5 pound weight would go. And then you got your magnets out here, and if you want, you can put some more pennies in for more mass. The problem when I put it on here, it's a bit of a wobble monster. I think you can see it on here. And I was trying every which way. Yeah, now you can really see it. If you put the 2.5 pound weight in, it becomes like twice as bad. I was trying every which way to correct that. You know, sometimes it's like the shop class stuff that just throws me. And you know, maybe a garage mechanic understood this like when they were 6 years old or something. I'm just figuring it out now. So the problem as I see it is this plate here is 1/10 of an inch thick, and so it's grabbing like 1/3 of this, and you would just have to have it perfect in order for it not to want to wobble up and down like that. But if you extend this out, just say extend a piece out like here and put in a second bearing. Now it would have to wobble through both of them, and as long as your axle's straight and this part's straight, then it no longer has the ability to wobble much back and forth like that. So it's like, oh yeah, so that's why they have 2 bearings on a skateboard wheel. I was out for a walk today. I saw a bicycle. They got 2 bearings on the bicycle wheel. I bet they have 2 bearings on a car wheel, and so on and so forth. Now another point, just to kind of, since I'm just talking, I'm putting the weight like this. So if I'm starting to get the terminology right now, that's going to be an axial force on your bearing. Now what these things are used to is running along the road. The skateboard bearing, the bicycle, or the car, with a radial force. And so it might be worthwhile at some point to set the thing up horizontally instead of vertically. But I'm just trying to get 2 to 5 pounds on here. You see like these skateboarders, they're like 160 pounds, they go 5 feet in the air and boom, and land on there. So the forces this thing can handle are quite high. And I think even going in a direction that it's not used to, unless I'm putting like 50 pounds or something there, I don't think it'll care. But what I'm thinking is, let's just go slow and steady, try and be the tortoise instead of the hare. I didn't want to reverse those two. And so for the next one, and this is what's making that noise because it's printing right now, we've got this thing. And you'll note it looks an awful lot like that one. There are 3 differences. One is focus. Let me get this out of the way. This is now 0.9 instead of, this was 0.6. So we can add 50% more pennies. Now the other 2 things that I did, let me show you. You see where these are like this, with this one up against there for your second row. So I moved the second row to up against here, and this allows your second row to be out closer towards the periphery. So when you put weight in there, it's going to add more momentum than putting weight in there. So that's a little bit of a benefit, and we can add 50% more pennies. Now the other thing I've got are those. There's 4 of them. So what are those for? Those will be for this, which will fit in the grooves that I put there. And so just to show you the idea, now this rotor I didn't think to put any grooves in, but I just printed a little lid here. So you see that goes on like that. Ain't that pretty? Now, what does that do for us? Problem I'm having, and it may be because the rotor's, wobbly, or it may be the diamagnetism of the copper. I'm gonna put, right now I've got 2 of the copper clad on the bottom, the rest copper. As I do more of this, I'll put, like 4 or 6 when we can fit more pennies. And I think that will really get rid of any issues from the diamagnetism of the copper going past the coils. But when I spin this thing, I want to spin it at least 1,000 RPMs, because you need a short pulse. And even with taking the duty cycle as narrow as I can, you still want it, ideally you'd want it spin at like 3,000 RPMs with a, but at least like 1,000. And the problem I have is I'll get up to, well, really I see it like around like 1,200 or 1,400 or something like that, and all of a sudden, ping! And I say it's the diamagnetism because it's never one of these that flies off. It's always one of the pennies. And I don't know if it's because of being Captain Wobbleshaft here, or whether, as I said, that the pennies are interacting. But put this on here, put a little tape there, and then put some electrician's tape around the outside. So there's no real forces driving the pennies out. So they're just sort of, I think when it becomes unbalanced, boom. And even just having this thing taped on there, I think you can run it safely at 1,200, 1,500 RPMs. I'll probably shoot for like 1,000. And then, and then by the next video, hopefully the next rotor will be completed and will be good. Fingers crossed. And then we can, anchor this thing in like that. And then once you do, once you have it set up like that, is you can do all your test work. And if you finally are at some place where, all right, this is a good one, then you just glue these parts in, or maybe parts there. And even then, see, what I don't want, one of these are feather pennies. I don't want to get a bunch of glue on them. And I don't want to get a bunch of glue. Granted, it was like $7 for all these magnets, the ceramics. But still, once you get a bunch of glue, you got to like scrape it off for the next project. You got to break the rotor in half to get it out. So until you really know what you want to be able to take things apart and put them back together, but you don't want things flying off. So that's what this is about. And this is just a little jury-rigged thing so it can spin a little faster without me having to worry about a penny flying off. But you can see how nice that's going to look. And you see all of these, not all of them, but I've seen at least once, and occasionally I think notice some more, where, oh, it's a free energy machine, and they like have some spring or something like that, and then some wood, and they just never show the coils or the magnets. So you're like at a point here where you can't see what's inside the rotor. So as I said, just go to where you're adding 50% more mass instead of trying to go straight to like 5 times more mass, and that'll be again looking at the issue of the mass of the rotor. But another thing, if I start to be able to nail down with 3D printing where this thing's not wobbling all around and it's going all right, is we've looked at the air gap a little bit, but it would also be nice to look at what should be the spacing of these magnets. Should they be in like this? Should they be right next to each other? Should they be out like that? And I think you could probably get away with a little bit closer spacing. Now with monopole, it's going to behave differently, because when you bring 2 norths in like this, it starts shooting a south out, what Bedini would call an imaginary south. And so the short answer is I don't know. And I think it'll be different for monopole and bipolar commutation. But that'll be fun to look at. And the closer you can get those in with it still improving on all fronts, then that's much better for reasons we can go into in another video. So the last question will be, what kind of wire gauge do we want to use for this first battery test going? I've got some 26 gauge wound, some 24 gauge wound with the ferrite cores, and some 22 gauge wound. I'm guessing this is just ballpark. 26 gauge would probably be about 15-20 milliamps. 24 would be like 20, 30 milliamps, and the 22, 30 or 40 milliamps. So I'm probably going to go with the 26 gauge and the 20 milliamp hour draw, which means that the machine will probably run for like 10 hours at least before it goes down. And one of the reasons I'm going to do that is because, again, even once I take those things in, if I'm using the 22 gauge, even when I bring the duty cycle down as narrow as I can get it, I think it's going to want to spin at like 1400 or 1500 RPMs. And I'm just not sure. Maybe I can do that, but this will probably spin at like 800 or 900, and so that'll be a little bit more reasonable, although it's going to take a long time to do. And I'll kind of tell you a little secret that may be true in the back of my mind here. I think it is. But, okay, so as you go with thicker wire, you're actually at a slower rotational speed, a slower number of hertz. Now, again, with the core, it's a bit different, but this is just what I've seen with the LCR, that the maximum, the highest Q factor is, maybe 4,500 with this one, like 4,000 with the 24, and 3,500 with the 22 gauge. So, 18 gauge, maybe like 3,000 hertz, which, again, that's hertz, and then you're talking RPMs, and so those are not the same. But you can adjust the duty cycle. So what I'm getting at is that, especially as you go with the thicker gauge wire, you could get to a point, maybe it'll be at like 3,000 RPMs or 4,000 RPMs, or if you go any faster, the spike's not going to do any better. It'll start doing worse. So at that point, if you wanted to add more, amperage in, you're going to want to put resistance on this thing, because you don't want it spinning any faster, not just because it could fly apart, but also because the spike will actually be getting worse. So, then you think, how do you want to put some resistance? You put like a fan on it, like Bedini has shown in one of his videos, a big fan on one of them, or do you do something else for the resistance? So that's kind of another interesting thing to think about. Or to put it more bluntly, right now, I'm just going to run this, capturing the spike, but at some point you want to start putting some pickup coils in, charging batteries with the pickup coils. They charge real nice. I've seen that before. I find they charge better than what I was getting off the spike the last time I tried it. So, let me stop here for now. I need to do one more battery. It'll be, well, I've done battery 2, battery 3, so it'll be battery number 1. Then we'll have one battery and 2 that will charge. We're not going to put any resistance on it in terms of a load to do some battery charging with a pickup coil. We're just going to look at this, and I just want to ballpark. Am I getting like 10% back? Or, maybe I'm getting 110% back. I have no freaking clue. And now finally I can test it. And I'm hoping it's at least like 50%. So we'll end the video once it's ready to go, and I'll just show you it charging the batteries, and then in the video after that I'll let you know what happened. Unless it's like 2%, then I might be too embarrassed to tell you. But I'll let you know once we're good to go here. All right, not quite powering the batteries yet, but if I can get this thing to spin true, here's the previous one, here's this one, and if I can get it to spin without wobbling, I think we might have a winner with this lid idea. I'll just show you. I mean, once I have the thing like that and I press it down, I have to use a, it's still not down. I have to use a knife to pry that thing out of there, and there's no glue involved. So this is good. You know what? this is bad. I said, don't count your chickens before you hatch. There's no place for the axle to go through. Everything else is beautiful. This print only took a half hour, this part. This one took 3 hours. Ah, fun. As I said, it's always the shop stuff, or me just being an idiot. So there's a bit of jury rigging, but I think some of this I'm going to hold on to going forward. So those are just little bits of rubber band, and then we press the top down there, and that just helps snug everything in. And right now there's just going to be some tape there and some tape on the outside. But as I think I've already showed, I've got a 3D printed one where these things fit into slots, and they fit in nice and snug. So this looks all right, if I do say so myself. And, you know, for the 99% vast majority part, all the forces on your magnets and your pennies are radial that way. It's just if this thing's wobbling like this, you can get some axial force where if you don't have something, then a penny's going to fly off. So I bet you could spin this thing, you know, easy out to 2,000 RPMs. We're not going to do that on the first one. With the first one, we're just going to do the battery test with some really thin wire. And I don't know, it might be going 800 or 1,000 RPMs. But then I'm going to be going thicker gauge. I want to look at how the battery charging might change with different gauges of wire, in which case we're going to be going faster. And yeah, so let's get it spinning.